Hello and welcome to the Online Mechanical Engineer. Today we'll be delving into the discrete stiffness method, which is one of many methods used in finite element analysis, or FEA for short. This session is designed to help you develop a fundamental understanding of these essential concepts, so without any further ado, let's begin. Consider a simple one-dimensional bar element 10 meters in length under axial load, fixed at one end and subjected to a force of 100 kilonewtons at the other. The question goes as follows. Calculate the displacement of the bar and any associated reaction forces. The structure's properties are as follows. Its Young's modulus is 200 gigapascals, its cross-sectional area is 0.001 meters squared, and its length is 10 meters. The first step to analysing this problem is simplifying it. To do this, we will first divide the bar into smaller elements and have each element represented as a spring. For simplicity, let's divide it into two equal elements, each of length L divided by 2. Now the structure has been simplified, you will want to label the springs representing the 5 meter long segments of the bar. General practice is to label the springs K1 and K2. Now label the nodes which connect the springs to the fixed position on the left, the node which connects the springs together, and the node which has the external force applied to it, node 1, 2, and 3. For a 1D bar element, the stiffness matrix takes the form as shown. Positive K, negative K, negative K, positive K, where K in the matrix represents the constant stiffness values of the bar element. Now we must calculate the stiffness constants which will be inputted into the stiffness matrix of the bar element. K equals Young's modulus times cross-sectional area divided by length. There is also an alternative equation which is Young's modulus times second moment of area divided by length cubed. We'll be using the first equation for this example. So let's now plug our values in. So E equals 200 times 10 to the 9, A equals 1 times 10 to the minus 3, and L equals 5 meters in length. And the value is 40 times 10 to the 6 newtons per meter. Now we must combine both stiffness matrices of K1 and K2 together. To do this, first identify how many nodes you have in the problem, which for this problem we have 3 nodes. Next, you must identify the degrees of freedom the structure has, which for this problem the structure can only move in the horizontal direction, so it has 1 degree of freedom. Now multiply the nodes with the degrees of freedom, so 3 times 1, which gives us 3, so our combined stiffness matrix is a 3 by 3. Knowing this, write out nodes 1, 2 and 3 to formulate a 3 by 3 table. If we consider the first bar element represented by K1, we can see that it is connected to nodes 1 and 2. So we will fill in this combined stiffness matrix with the general stiffness matrix we previously discussed. Now consider the second bar element represented by K2. We can see that it is connected to nodes 2 and 3. So we will fill in this combined stiffness matrix with the general stiffness matrix we also previously discussed. And here we have it on the right hand side, the completed stiffness matrix. The next step is to now formulate the global stiffness matrix. This takes the form of the stiffness matrix, which we have just previously discussed, multiplied by the displacement matrix of the nodes, which will equal the force matrix. Now we can apply boundary conditions. Node 3 is experiencing an external force of 100 kilonewtons. Node 2 has no external force applied, and we expect a reaction force on node 1 to maintain structural equilibrium. Node 1 will have a displacement of 0 due to it being fixed to the wall. This allows us to cross out the first horizontal and first vertical lines in the global stiffness matrix, as U1 represents the displacement of node 1, which as previously discussed is 0. Now we can assemble the reduced stiffness matrix. This is what's left in the global stiffness matrix after the boundary conditions have been applied, here circled in green. And here we have it, the reduced stiffness matrix. Now fill in the reduced stiffness matrix with the known values. Because K1 and K2 are the same, simply put 40 times 10 to the 6 times 2, then minus 40 times 10 to the 6, then again minus 40 times 10 to the 6, and finally 40 times 10 to the 6. We can also replace F2 and F3. F2 has no external force, so is 0, and F3 has a positive 100 kilonewton force. Now let's solve the displacements of node 2 and node 3. This can be done in two ways: either multiply out the stiffness matrix with the displacement matrix and set them equal to the force matrix, then solve the simultaneous equations, or if you have a calculator with a simultaneous operating solver, use that to solve the displacements of node 2 and 3. And here we have it. U2 equals 2.5 times 10 to the minus 3 meters, also known as 2.5 millimeters, and U3 equals 5 times 10 to the minus 3 meters, or 5 millimeters. And of course, U1 is just 0 because on the left-hand side of the structure, it's fixed. Now we must bring back the global stiffness matrix to solve for the unknown reaction forces. So here we have it. So we know F3 is already 100 kilonewtons, and F2 we're going to find we're using the global stiffness matrix. Find F2, the first thing you're going to do is multiply the second from the top horizontal line out. So that's going to be minus K1 times U1 plus K1 plus K2 times U2 plus minus K2 times U3, which is all going to equal F2. Once you plug in all your values, you then get F2. As expected, there is no reaction force on F2, nor is there any external force, so therefore F2 equals 0. Now, just as we've done previously, we're going to use the global stiffness matrix to find F1. So what we want to do is take the top horizontal line, so we're going to do K1 times U1 plus minus K1 times U2 plus 0 times U3, which we're all going to set equal to F1, and we should expect it to be minus 100 kilonewtons, so that the structure is in static equilibrium. And here we go. So the last part is just checking that everything adds up and makes sense. So we're just checking for static equilibrium. So if we add up force 1, force 2, force 3, which are acting on 1, 2, 3 nodes, it should all equal 0 for the bar to be in equilibrium. And here I'm just writing out the displacements of node 1, 2, and 3. Just for clarity, here is the completed question with me adding the displacements of where they go. And as you can see, the two reaction forces acting on the beam itself. If you found this useful, please like and subscribe to be notified when I've uploaded new content. The next part to this 4-part series, the direct stiffness method, will be about understanding how to calculate a beam's deflection when a bar has 2 degrees of freedom. Thanks, have a great day.